So imagine we have a current that in the shape of a wire, and it's an irregular shape. We only concentrate on the piece of the wire. Normally the wire extends long, but we only concentrate on the portion of the wire between the point, let's say A, and the point B. So the current flows at a constant rate, or it may change, of course. And the question is that since we know that moving charged particles are creating magnetic field at some point away from them, and we just discovered how to find the magnetic field, so why not we now try to find a way to calculate the magnetic field created by this portion of the wire at some point. Let's choose the point to be here. There are many charged particles that flows through this wire, and we know that every piece of charge can create a magnetic field at some point away from it. So, but our aim is to express this magnetic field not in terms of the individual charges that are flowing through this wire, but in terms of the wire itself and maybe the length of it. Okay, so we will concentrate on to find this magnetic field in terms of the parameters, the current I, the starting point of the wire, the ending point of the wire, etc. I will just write away the result, that how to find this magnetic field at this point. Let me show this displacement vector R. Just pick up a piece of this wire from extending from point A to B. Let's take this piece to be this one, and it is infinitesimally small length. Since it is infinitesimally small, you can think this portion, this very small short portion of the wire, as a straight wire, okay, as a straight portion. I will just call this portion to be ds. This is what normally we do. ds usually stands for an infinitesimal small length element, so that's why I call it. But we take this ds to be a vector. Okay, well, the only thing is that that gives direction to this small length element is the direction of the current. Since the direction of the current flows in this direction, I will take the head of the vector over here and the tail is here. So, well, the next thing, as you can imagine, that we have always do for continuous sources is to express only small portion of this finite length of wire extending from A to B. We only consider the very small portion of that we call ds, and if we can express the magnetic field created by ds to be dB right at this point, okay, and if I can write down an expression for dB, then of course the total result that the magnetic field created by this wire extending from A to B is going to be an integral. Okay, so what is this dB? And dB I will just write away to be this is an expression, empirical expression. This constant is always there. It's mu0 divided by 4 pi, the magnetic permeability of free space, divided by 4 pi, as it exists on the expression for the magnetic field for point charges. So it's always there. And I, well, remember the first vector was v for the point charges, but the first vector for this infinitesimal small current to be ds vector, and this is going to be cross product by r, the displacement vector that extends from ds to the point in question that we want to calculate the magnetic field. So this is going to be divided by r cube. Okay, so this is the complete expression for, well, it's not complete. This is the expression for very small element of this finite length current carrying wire at this point. Well, of course, this ds is going to change from starting point to the ending point B, and we'll consider all these ds's that are added head to tail. There are many ds's starting from A, and if you add them all from head to tail, you will just complete the wire. So, I mean, you can imagine that the total magnetic field just between the points A and B, the wire extends from point to B, from point A to B, is going to just be the sum of all those dBs. And the sum, of course, can be expressed, or should be expressed, in terms of the starting point and end point, since we are talking about DS's, and we are going to also, if the current is does not change with the position of the wire or the position of the ds, this can be taken outside the integral. So for constant currents, mu0 I divided by 4 pi integral ds cross the r divided by r cube. Sorry, this is going to be r cube, and it's from A to B. This is the limit of these are the limits of the integration. So this is the expression for the total magnetic field created by a current carrying wire which extends from point A to point B. You can enlarge, okay, you can choose these points as you wish, as larger or smaller or whatever you want. So that's it. I mean, this is the expression. Of course, it looks like a very tedious expression. You can just think of, first you have to take the cross product, then you take the integral. This looks like a very complicated, but if you think about it, I mean, we will see some examples. For certain geometrical shapes like straight wire, like a circular wire, etc., this integral is going to be very simplified, and it's a very simple integral and very simple cross product you will take. Okay, so that's it.